Hello everyone, my name is Yujie Ren. Today I will be presenting our work, CrossFS, a cross-layered direct access file system. This work is done in collaboration with Changwu Ming and Sudarshan Kannan. The storage technology has entered the microsecond era. Modern storage devices have considerable compute power inside. To access a file, an application needs to enter the OS kernel through multiple software layers before reaching the storage hardware. So, file system performance becomes critical. When applications are sharing files, improving concurrency is important. There are roughly three categories of file system design. Kernel FS, where the entire file system is in the OS kernel managing data and metadata. User FS disaggregates data and control plane operations, where the data plane operations bypass OS kernel. Firmware FS offload the entire file system to storage firmware to provide direct access for all I/O requests. However, there are several limitations. The kernel FS suffers from high system call overheads, could not utilize storage-level compute resources. User FS, though it provides direct access for data plane operations, the storage-level compute is not utilized. Firmware FS provides direct access, but it cannot utilize powerful host CPU at all. None of the above five systems satisfy fine-grained concurrency control. CrossFS satisfies all of those four properties. Concurrency is critical in several data center HPC applications and widely used benchmarks that share files across threads and processes. Now let's look at what is happening in file system for file sharing. There are two threads accessing a shared file, even if they write to different blocks. Once thread 1 holds the inode level lock, thread 2 needs to wait until thread 1 finishes writing and release the lock. To analyze the impact of inode level lock, we perform an experiment that concurrent reader and writer threads randomly accessing a shared file. As the number of threads increases, the throughput does not scale very well because they are limited by the inode level lock. I will show how CrossFS could achieve higher performance. To break those limitations, we propose CrossFS, a cross-layered direct access file system. In contrast to state-of-the-art solutions that separate control and data plane I/O operations, CrossFS disaggregate file system components to exploit host and device CPU resources. CrossFS bypasses OS to reduce software overheads. We also introduce a file descriptor-based fine-grained concurrency control. We also designed a file descriptor-based I/O queue scheduling and crash consistency, which you can find out in our paper. CrossFS disaggregates file system components across I/O software and hardware layers. The kernel component is responsible for file system mount, setting up I/O queue, and security. Library FF, with each application that utilizes host CPU, dispatches I/O commands and also performs fine-grained concurrency control. FirmFS runs inside storage device, utilizes storage CPU, scheduling I/O requests from the I/O queue, and perform block managing, journaling, and permission check. CrossFS bypasses the OS kernel for most data and control plane operations and goes to OS only when necessary, such as file setup. Now let me introduce the fine-grained concurrency control in CrossFS. As we analyzed, inode level reader-writer lock is the bottleneck. Hence, non-overlapping writes could be in parallel. We observed that different threads could open different file descriptors for shared file. So, file descriptor is a natural abstraction for dispatching I/O requests in parallel. CrossFS aligns each file descriptor with a dedicated I/O queue. We note this as FDQ. Here is an example of two threads are accessing a shared file. When thread 1 calls open, an FDQ is created. Similarly, thread 2 gets its own FDQ. The write requests from different threads could be dispatched in parallel without interfering with each other. You might immediately ask, what about overlapping writes, when two threads write to the same or overlapping blocks? To resolve the overlapping cases, CrossFS used the interval tree data structure. An interval tree is an augmented balanced binary search tree. Each interval tree node depicts an interval with the range of the interval and also the max value in the subtree to help look up and insert operations. We use interval tree to store I/O block ranges for in-flight requests. Here is an example with overlapping writes. Each I node has an interval tree in the library FS. In operation 1, thread 1 writes to range 0 to 4K. The library FS logs the interval tree, inserts an entry of 0 to 4K range with the atomic timestamp counter, and then release the log and finally put this I/O request to its FDQ. In operation 2, thread 2 writes to range 4K to 8K, which is a non-overlapping request. Similarly, library FS put operation 2 to its queue. Operation 3 is an overlapping update with operation 1 for range 0 to 4K. When the library FS is looking up the interval tree, it finds out an earlier request operation 1 is overlapping. Hence, it updates the interval tree node and inserts operation 3 to the queue of operation 1 because they are overlapping. In this example, operation 1 will be marked as no op because operation 3 is completely overlapping with operation 1. By using interval tree structure, the log is only required in the interval tree operation, so the critical section is really short in CrossFS compared with inode level log. CrossFS converts file concurrency control to a queue ordering problem. Once the I/O requests are ordered, the firmware FS dispatches requests from queues in parallel. To evaluate CrossFS, we use multi-core system with Intel Optane persistent memory as our storage. Due to the lack of programmable flash storage hardware when developing CrossFS, we emulate firmware FS as the device driver in the Linux kernel. We evaluate CrossFS with state-of-the-art file systems. We developed the micro-benchmark that multiple readers and for writer threads randomly access a large shared file. The y-axis shows the aggregated reader's throughput. As the number of reader threads increases, existing file system suffers from inode level log or software overheads. By removing inode level log and provide direct access, CrossFS achieves up to more than 4x throughput gain for reader threads. For writer's performance, we use the same micro-benchmark. The y-axis shows the aggregated for writer throughput. CrossFS shows up to more than 3x throughput gains for writer threads, because non-overlapping writes to a shared file could be dispatched in parallel. We then evaluate on real-world application RocksDB with dbbench. CrossFS is able to achieve more than 2x through random throughput gains from fine-grained concurrency and direct access. To conclude today's talk, storage hardware has reached the microsecond era. Providing direct I/O and utilize host and storage level compute is critical. And fine-grained concurrency control is important for I/O scalability. Thanks for your attention.